Hello and welcome to Chemspec Digital 2021. I have the pleasure to introduce the next presentation in the RSC Lecture Theatre. But before I do, I would like to point out to you that we are recording the presentation and it will be available to view on demand later on. Attendees are invited to write questions into the chat function. And I will read them out and present them to our guest today. But without further ado, I will now hand over to Wouter Stam of Fluid, who will be presenting a continuous flow production 10 years of progress. Over to you.
Thank you. Thank you for the introduction. Yeah, I'm sorry I changed the title. I think back in the day when we started with it, it was 10 years. Nowadays it's 12 years, so also another title because 10 years wasn't really added, but I will add it in the future. So we are focusing on industrial applications, but all continuous. So how do we go from batch to flow? What is the best technology available? And so we started more than 12 years ago now, and going from all kinds of different phases into flow production at the moment. And that's where I actually wanted to go to look at that from a different angle. And so if you look at our goal is to look at flow solutions, and then we're going from a scale up, from development to production. So from batch to flow, from flow to scale up to the main goal, production. And if you look at that from a different angle, we always say we start with production. So what would be the main goal? So how do you want to produce? How much do you want to produce? In contrary to a batch plant, you don't have to choose at once your throughput. You can make more units, and we can also on forehand look from that. So our goal is to start with the production, then of course safety, which is a prerequisite always, and footprint. Footprint is really important aspect. So the plant has to fit into an existing infrastructure. It's rarely that we see that it needs to be built in a new facility. So to fit it in between existing batch vessels or add it there is a big aspect of production in flow. Capacity, of course, capacity has to fit. We see high-end materials, chemicals, pharmaceuticals, and of course for some pharmaceuticals, time to market. So you could really fast scale up to the production side without losing any valuable time there. I think that was also how I started back in the day at a biotech company. Wanted to go to flow, calculated we could get there in 6 months earlier. Unfortunately, they didn't do that, or fortunately, because then so how I started Fluid in the end. Equipment, of course, reactors, but also the whole aspect, pumps, flow meters, control, also the integration with the DCS system, for instance, and also the hookup with, for instance, downstream processing. Procurement is really important nowadays. I think even better, or even more important, as it's hard to secure raw materials, or let's say specialty items, and documentation. So for pharma, GMP documentation is really important, but in general. So legislation, we see that if you have a operating plant and you want to increase production, it's very hard to do that under the same umbrella of legislation. So by going to flow, you increase your volume or decrease your volume actually. So you can stay within the same permit. That's a really important part. So we see that there is to circumvent or to use the same permit, going to flow is a very important aspect. And there we say that we have to apply the best available technology. And that's the available technology in the market. Of course, you can always look into an option there or develop something yourself, but that always takes more time. And portability, so to move it around as a whole, or also as being a part, so a pumps kit, a reactors kit, back pressure skid. So that's where we see that the portability, the multi-purpose, combining it is more and more important. And of course, we see besides multi-phase or normal single-phase chemistry, we see multi-phase liquid-liquid, liquid-gas precipitation reactions being more and more important. So if we look at flow solutions and the best available technologies, we see here an example. This is a full GMP ATEX production facility with pumps, reactors, residence time units, automated control, everything. So if you go for optimization, you have to look at the process side, but also at the intensification side. So the chemistry, the equipment, the throughput, it all has to fit. There again, you look at the safety part, automation. In this case, it's integrated into the DCS system of the customer. So we make the junctions or the connections to there, do a close collaboration together with the customer. This is key, especially in the beginning. So how are you going to build it? What is required? What do you need? And there, this always takes a substantial effort from all parties. So that's you have to combine the engineering, make the P&IDs, 3D drawing. So for this one, you make a 3D drawing, does everything fit? And then we even make a mock-up model to go through the plant to actually see if it would fit. And then again, the procurement, you have to manufacture it, the documentation, and ship it, integrate it, and a really important aspect to make sure that it runs maintenance and support. So we said here it has to fit, it has to fat, it has to sat. And this is I think a little over 2 square meters of footprint. So if we look at going from production, so going from production down to the beginning or going from the beginning up. So how was it done? How is it done? How can it be done? I think you start with the chemistry in the early phase and then test in the lab. So there's a common knowledge in batch, common knowledge in lab devices, but a common knowledge in flow devices in lab. It's getting there. There's a lot of good work done nowadays by academia and also from Vaportech, Chemtrix, the lab, beautiful lab units that are working there. And then how do you scale it up? So when we started, the holy grail was you do 100,000 or 10,000 small microreactors next to each other, and that is how you can produce it. Also, we thought that, but in the end, it doesn't work like that. You can scale it up, but then make parallel units, but it should be a few and not 1,000 or 100. Depends also a bit on what is the optimal production range, what is the value of the product. So if you look at continuous manufacturing, the considerations that you see is, has the chemistry fit flow or should flow fit chemistry? And this is, very strange question perhaps, but it's what we see on daily basis. So if you have a vessel, then you have to fit chemistry to the vessel. And if you have a flow reactor, then you could fit your reactor to the chemistry. So if you look at that part, I always say the dynamic is not in the vessel, or it's in the vessel normally, but the dynamic is not in the reactor, it's in the pumps. So if you control the pumps, if you control the temperature, if you control the pressure, you can always say that you make the same product. And even going from that, you can say that the drivers for flow, even for the same kind of chemistry, they are different from case to case. So would it be legislation? Would it be yield? Would it be safety? There could be a number of different reasons that a similar case has a different approach. Anyway, the main goal is always to reduce your expenditures, your capital and your operating costs. And with that in mind, if you go to the production side or go at the start, it's very wise to take continuous process at a starting point to go that way, especially in pharma. And I think that's where the whole chain from lab to pilot to production is growing. It's also partnerships. I think people might want to do it alone, but you cannot. You cannot do it alone. It's if you do the chemistry and engineering to convert these processes to flow, we focus on the engineering and the manufacturing of the flow skids. And we take the best available technologies, the best available pumps and reactors, could be our own, could be others. So we have worked with Chemtrix reactors, with Fluidtech. We also work with Zyput for the downstream processing part. And that has to be scalable from lab to pilot to production. And to do that, we have to understand the chemistry. So we have to understand what does the customer want to do with it, and then engineer the best total solution. And previous slide, I also explained it. It's always in close cooperation with the customer. So if you sometimes a process is tendered, and if it has to be engineered, that's always on forehand very difficult to give a good feedback on the tender. It should be a close collaboration on forehand. What do you want? This is always interesting discussions. And then select the best technology for the application. So that is here are a few that we work with. I named them Fuji Techno for the high pressure pumps, and well, there's many more. If you look at the flow reactors there, you can typically say there's two types. It's a static or a dynamic reactor, and I named a few. I probably miss a few, or there's some changes there, but if you look at static flow reactors, they're from Chemtrix, Corning, plate reactor from Eerveld, and when we started from Alfa Laval, and also T-pieces, so T-pieces with a coil, R&D, homemade. We've seen very nice examples from R&D departments, they work with that. And if you look at dynamic, so for mixing multi-phase applications, AM technology, our own spin, I'll come back to that later, and the oscillated flow reactor from Nitec. So they're all different reactors with different application windows. So you have to select them on a need to use basis. And of course, I would be always trying to sell my own, but if it's not needed, then we have to search for the best one. So we better turn it around and say what is needed for a certain application, instead of pushing the own technology. What we did also in the early days, but that could be another story. I think there's a lot of chemistries converted to flow, and a lot of chemistries also being converted to flow. And if you look at a lot of these articles, I think there's a whole lot of articles that are published on flow lately, very interesting ones. And how do they end up in the production range? So for us, we're always looking at mass transfer limited reactions. So if it has to be, the temperature has to be controlled, or longer residence time is required because it's diluted or it's low in temperature. So exothermic reactions, and then specifically for us multi-phase. So gas, liquid, 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 gas, liquid, liquid. And what we see coming up at this moment is precipitation. So there could be biphasic or single phasic. But if there's a precipitate there for dynamics, our dynamic system, that works really well. So we have converted a few, I named them here, organometallic, so butyl lithium, hexyl lithium chemistry. That's where we have strong belief in, that has a great application window. Nitration, single phase or biphasic nitrations, diazotizations, halogenations. So it's all these kind of chemistries. They are exothermic, toxic, dangerous. So there's a high-end need for safety, for controlling these type of chemistries, and that's I think also where you end up in the high-end chemistry with this type of flow processes. So to show a few of the processes, products we have been working on, these are 3 production skits. This is a GMP full ATEX. It's a there's a Y mixture in with residence time units, and this has a few liters a minute of throughput. This is a SpinPro gas liquid, high exothermic one, and this is a high pressure full Hastelloy. This unit here is also fully ATEX. And the best here, these are all recurrent flow production skits. So if it works, if the benefit is there, then there's an expansion, another one. And this is, I think, very important to show that there, when it works, it becomes recurrent. And it's not a one-off type of work that these companies are doing. So to give some more detail on this one, this is GMP full ATEX. It has to fit into existing infrastructure and has 24/7 operation. And this one is very full. Yeah? I've probably explained it before, but we had to fit it into the industrial elevator. So it has 1 unit to fit in the elevator. That's why it's so full of the whole operation. Again, we made a mock-up, we did it, we tested it, and this was also done in very fast time. I think we did eventual construction in only 2 months. So from start to finish was within a year. I would not recommend to do that every time, but this was a very, very fast, interesting project. Here you see standalone. This is a standalone with a HMI control locally, thermostat, SpinPro, which is a gas liquid, exothermic gas liquid reaction. And there you get 99% raw material efficiency, also fit in existing infrastructure, and great OPEX and CAPEX reduction. Again, here, perhaps this one should be on top, safety first, so no risk. This week, we made the 2nd reactor in and the 2nd unit there. I didn't have a good picture, otherwise I would have put it in. So this was actually a little bit too early. But on forehand, I think where we started with, where do you want to use your process for? How do you want to produce it? And how do you want to produce it in future? So we build this together with the customer to double the production output already on forehand. So we took the unit out of production, put it here, build it, tested it, and put it back in. And then you have a double the production output without, again, changing your infrastructure. So it's still in the same footprint. And if they want to produce more in the future, they could duplicate this operation or place it somewhere else in the world. This is a full explosion-proof Hastelloy unit, also GMP. So this skid that's on the side with the control and a thermostat is outside of the GMP area and outside of the explosion-proof area. But this is a high temperature one, and it's a dedicated built unit to test several chemistries. And I think this is a one that you can expand. You could use for longer productions, for shorter tests. It's partially automated, partially manual. So this is another example where the customer wanted to use it as a multi-purpose unit. The other one before were for one dedicated product. So this is a multi-purpose application for high temperature ranges. So we go to our own dynamic reactor technology. We call that SpinPro. Here you see 3 reactors. These are all in 24/7 production, where you can see that the residence time would be controlled by the flow. and the mixing would be controlled by the rotation speed. So the flow and the mixing is controlled independently. And to take off the heat, you have integrated heat transfer. And this is a proven technology. We have multiple plants running with this technology in various industries. And to explain on that, if you on top here feed in a water phase, an organic phase, it flows through the reactor and you mix it by the speed of the disk. So your residence time is how fast do you pump it in, and your mixing is how fast do you rotate. And we can control that by integrating heat transfer. It can be co-current, counter-current, parallel, and we have temperature probes on either inlet, outlet, and on either disk, which can be operated modular, easy to control, easy to scale, safe operation, different materials of construction. And well, to give some insights for the technical guys, I still was one of them. So it's always interesting to talk about how does it work? How does the principle of the SpinPro work? So if you take one disk and you look at going from the top, going out in the bottom, you would have a certain plug flow regime from the center out. And depended on how fast you rotate, what kind of material is it, how fast do you flow, this will at a certain point cross over to your CSTR regime. And that's where you have your best mixing, so where you have the eddies. So if you take apart here at the edge where your mixing intensity would be the highest, you would have very small vortices, very small eddies. And by rotating at around 2000 RPM, you would be already gaining 1 million Reynolds. So if you have two phases, organic water or a water phase and a gas phase, the gas and the two phases get dispersed very well, and you get a very high surface area for fast transfer, so for fast reaction. To do that, you have to take off the heat. I have a movie that shows it, and started.
The chemical reactor is at the control allows reactions to proceed under process-intensified conditions, making the spinning disk reactor unique in terms of efficient, safe, and flexible production.
I understood that the sound was out and came back on the last, but don't be worried. If required, I can always show it again, or you can also find it on the website. To show, we have two flavors. We have SpinPro R10 and R300, and to give some idea on production output, if you have 1 second of residence time, then from this the smaller one you get an espresso per second, and for the larger one, if you have 1 second of residence time, it would give you a cappuccino per second. Of course, better mix than you show here. But if you look at throughput, this would be 70 liters an hour with 1 second, and this would be around 800. So what we see is that the operation in this case is the tens to hundreds of liters an hour of high-end valuable production. And it depends on what you want to do with it, how is this, but there's always an optimum on residence time and production output, of course. To show an example where we started with, this is the 3 reactors that I showed before. This is a 3-phase reaction with a gas, water, and organic. And there we were able to reduce the pressure, so it had a headspace, and then we could introduce the gas into the spin pro reactor. So there was a very low pressure required, but no headspace. So there was no high volume of high pressure toxic gas. So the safety increased and the permit was still maintained. Besides that, there was high selectivity and productivity with a very significant capex reduction and also significant opex reduction. Again, here we were able, together with the customer, to look where do we go in the future. So they anticipated on 50% production increase. So here you see there's the opening to put the reactor in, and at a certain point it was added. So there was an ease of integration in existing infrastructure. So here is a explosion-proof cabinet where the plant is in. So the plant itself is not ATEX, but it was in a explosion-proof atmosphere. And on forehand, we were looking at the 50% expansion by placing the reactor back in it. So an ease of capacity increase, and again, fits for small footprint and existing infrastructure. Also for the R10, which is a lab, but could also be small scale production. If you run 30-40 liters an hour of throughput on high end, it could also be a production unit. This is a chemical inert, so it's a silicon carbide unit, and this one is plug and operate. So here is the thermostat with it, the control cabinets where all the electronics are in. There is the control module which can be taken out or put into the fuel cabinet, 2 pumps, and the reactor module with all the pressure, temperature, back pressure regulators. So this one works on gas, liquid, and is ready to use. So one of the things we strongly believe in, and we've seen that also works in the dynamic system, is organometallic chemistry, where we see that these operations are safer. You can also use higher temperature, which typically would not be safer, but here we see that it's much safer and more efficient. So we can go from cryogenic conditions to 0 or even ambient, which would be a win on energy savings if you don't have to cool to cryogenic conditions. And also higher yield. We see that there's more than 10% of yield increase using that type of chemistry. Precipitation can happen if you go to -15, -10 degrees. But here, because of the high shear, there is no clogging, and reduced also lower OPEX and CAPEX. I think in partnership with Albemarle, we did this, a lot of work on it, and the article is to be published in OPRD very soon. Another aspect is what we're working on. I already started with that in 2016. I think yesterday, Hans Gemoets also gave a very interesting presentation on photochemistry and flow, which is growing also very interesting. So there, if you can mix gas and liquid, why can't you mix light? So the fluid dynamic photon reactor actually works on mixing light very efficiently. So if you look at the Lambert-Beer law, if you have a stagnant layer, then light transmittance decreases exponentially with the distance from the light source. And there already flow solutions are a big improvement for batch in all cases, also for light reactors. But still, these technologies are most often static and still have to overcome stagnant layer. And we have proven and working on processes where we see that the dynamic photon reactor reduces the stagnant layer by more than 90%. So if you just leave a small part open, your efficiency of your light into the media becomes much higher and it's much more efficient. To conclude, we see that flow processing is a proven scalable from lab for screening up to high capacity for production devices. And what we see is there's much more out there than you know. If you have it running in a plant, then you don't want to talk about it because it's a competitive advantage. That's what we hear often. But combining chemistry and engineering knowledge, I think this is a very interesting one. So the chemists talk to the engineers. Also in flow, it's a challenge. I think that works nowadays much better. By building complete setups that are installed in pharmaceuticals and pharmaceutical factories in the world, this is proven. And the drivers for these processes, they vary, but they all have to reduce in investment and operational cost. And with that, I want to thank you and the presentation. Thank you very much.
Thank you very much, Wouter, for that insightful presentation. I do want to invite attendees to write any questions into the chat box if they've got any queries or want to come back to anything as part of the presentation. And Wouter, maybe do you want to show that video again? Unfortunately, the audio with the unmuting and muting didn't quite work. Maybe in that time there'll be some questions from the audience.
Yes, I will do. So I will start with that.
That would be, yeah, that would be great. Get the benefit of the audio as well.
The chemical reactor is at
Now it
the
works.
heart of the chemical.
Brilliant.
Reactions are typically performed in large vessels. The spinning disk reactor outperforms conventional reactor equipment, adding unique process controllability. This reactor consists of a stationary case connected to a motor. The motor drives 3 disks, which rotate at high velocities inside the narrow casing. 2 reactants are fed into the device from the top side and then flow around the rotating disks. The large shear forces provide very efficient mixing of the reactants. This results in high mass transfer rates, allowing reactions to take place in seconds. During the reaction, large amounts of heat are released. Cooling channels are integrated inside the casing to effectively remove this reaction heat. The combination of high mass transfer rates and the temperature control allows reactions to proceed under process-intensified conditions, making the spinning disk reactor unique in terms of efficient, safe, and flexible production.
Yeah. Excellent. Thank you very much for that. Then we got to watch the whole thing. And in the meantime, I think what was there was a question how interested parties can go into production.
Yeah, I think this is a very interesting question. This is what we see often there. If there's no knowledge in flow or if they're not used to flow, then it's how do you start with that? And how do you start with, do you start from the lab, what we talked about, or do you start with the production? So if you have a production issue, do you then look at flow as a solution? Or does that come from top to bottom, then going from the lab to the scale up, to the pilot, to the plant? I think that if you have production issues or challenges or want to double it or increase it, contacting any of the people in the community for flow is something to do. So just pick up the phone and dial in.
Well, I suppose on that note, thank you very much, Wouter. And there's the opportunity, if any of you in the audience have any further questions specifically for Wouter or for Fluid, please reach out on the platform and pre-schedule your meetings. And we've just got the rest of the day to still have meetings with the team. And of course, we'd like at this point to thank you to our presenter and thank you everybody for watching, and we'll see you in the next session. Thank you.
Thank you. Bye-bye.